Ah. Okay, now it is. Yeah. So Juan, what I did not understand is there was something also about YouTube in the. So you're going to record this also to YouTube or stream this to YouTube? So
yeah, we don't stream it openly. So but
yeah.
we use YouTube to keep a recording of the seminars.
Yeah. So I can also distribute the link afterwards, or
sure. Feel free to send it to.
Yeah.
So the link is hidden. So if somebody is looking for the talk, is not going to find it in the search.
Okay.
But it will work for anybody that has the link.
Nice.
Okay, so I should, so Juan, please guide me on what I should do in the seminar. I should turn on the projector and connect, right? And
yeah. So in the meanwhile, I'm going to record to the cloud. So you connect the beamer,
yes,
to the laptop. I already started the recording on YouTube.
Wonderful, thank you.
And then I'm going to make you host, Mohammed.
Okay.
So you have control.
Thank you. So I'm just turning on the projector and so it's turning on. It's coming. So then you'll be leaving just before we start, right? Or you're gonna
because here the next talk start at 11:30. So I'm going to send a reminder of the seminar.
Yes.
And it's a pity because the topic is very
very close to what you're doing. Yeah.
Yeah.
So I can watch the recording later.
Yeah. I need to go to the bathroom one more time. So okay. I'm gonna have a short bathroom break. I will be back. Yeah.
No problem.
Okay.
Okay. So how's the talk over there? Is it good? Everything working?
Yeah, very nice. It's the Spanish AGN community, so it's a more focused meeting than the SEA because the science is more common, but still it's a mix of people doing kind of different things. But it's nice because I have many friends that it's been some time that we haven't met. And it's nice to reconnect with people.
Yeah, I was impressed to hear that like the Spanish community has a specific AGN
yeah, because pretty much
there's so many people.
There is a big group in IAC, then also here in IAA, and also in Madrid, and they are also in many instrumental projects like SKA. There is a node here in Granada, even Horizon Telescope as well. They have a lot of. There is a big part of the collaboration that has a node here in Granada. So yeah. That makes so they make these meetings like every 2 years, I think.
Nice. That's good. And how long is it? How many days are you going to be there?
It's 2 days, but so it's 2 half days and 1 full day. So it's very short.
Okay, well that's good.
We
should set up such meetings for like the other disciplines we're working on. I didn't know that. It's a good idea. It's a really good idea to have this.
Yeah, because it keeps the local community connected.
Exactly.
So I think it's very useful to establish collaborations within the Spanish institutes.
Exactly. Yeah, which is
also for students.
No?
For students, it's a perfect scenario to give a talk before going to a bigger conference.
Exactly.
Yeah. Should we working again? Yeah.
Yes.
Now I noticed, of course, that the slide that I just added was complete bullshit. Let's remove it again.
Okay.
So could you connect the beamer, Mohammed? Did you have any?
I turned it on, but I want to see. Okay. Yes, it's working. Yeah, it's showing my desktop. I will just move the Zoom window to this desktop. Yes, it's working. I should just close my curtains. To be more clear, is your background? No, it's white, right? I'm Christian, so it's that bad.
Sorry?
The background of your slides are white, so
The background is white, yeah?
better, yeah. I'm trying to darken the room, so
Yeah, that will be useful because there are some slides that have black background.
yeah.
But the most of the slides, like the figures, I mean, you know, there I usually use the inverted color schemes. So black is the background color.
So now on your side, it's black behind yourself. So
behind myself here is black, yes.
Yes. So that's good.
But
yeah.
here should be the slides.
Yes,
Where so I also have a pointing stick then.
Oh, nice. Okay, that's good.
Yeah, it's very professional here. I really have to thank the organizers then officially for
it's much more immersive than a normal virtual talk.
Yeah,
this is the setup that they are using for remote teaching during installed here for remote teaching during the pandemic. And I asked kind of short notice to use it.
Okay, cool.
Yeah.
So you're in Leiden now. In fact, I just had a meeting with another student in Leiden just 10 minutes ago, I think. It was Juan Miro. Do you know him?
There's so many people here. This is incredible how big this institute is in terms of numbers of students, PhD students. I think 80 or somebody told me like
total volume is
the total volume, but this number of PhD students at
that already is sort of between 50 and 100.
Yeah.
Okay, so Juan, you're still here?
For a university institute?
Yeah, I just sent the reminder of the seminar.
Yes, okay, great.
So
okay, we still have almost 5 minutes. No one is coming yet, but they'll be coming. So
like usual.
Okay, so everything is working, right?
Yes, on my side everything's working, the project is working, and on your side everything is working as well, right?
I think so. Let me just try one thing to see that you can see the animation that I'm going to play. Oops. Obviously that
Yes, we see the animation. Nice. Yes.
And it's also like not lagging or anything. Good.
No. Okay. Very smooth. Yes. No, it's great. It's great. And Juan, on your side, everything is good?
Yeah, I started the YouTube recording and the Zoom recording. So, and I made you host. So now you have superpowers.
Yeah.
And when you finish, the only thing you have to do is to end the meeting for all, and then the recordings will stop automatically.
Okay, wonderful.
And if you have any kind of technical problem or anything, just write me and I will be checking the email just in case.
Okay, thanks a lot. Great. Thank you so much, Juan, for setting up everything remotely. It's
no, thank you guys.
Yeah, thanks.
Okay, I have to leave you now.
Yes,
we are starting here in a while.
Yeah, nice to meet you and see you again.
Nice to meet you, Christian. You have to come to visit us in Teruel. We don't have such a fancy technology for seminars, but the city is very nice.
Yeah. I contact you afterwards with respect to that. I have to finish my travel plans for this semester now, and then
Okay, perfect.
Just
have a nice time, guys.
Thank
See
you
later.
Bye. So I'll just right now the sound is only from my computer. I just noticed it's not too high for the whole room. So I'll just load the speakers. Okay, can you say something? Christiana, I'm just trying to see if the voice is good.
Yeah, 1, 2, 3, 1, 2, 3.
Very good.
I might speak a bit louder when I'm then in the mood, but
No, this voice is even is a little too
Yeah,
much.
yeah.
I'll decrease it on this side.
Yeah.
No, yeah. Now the speakers are on. It's good. Your voice covers the whole room. Nice.
Just put me on mute.
Yeah. Okay, so now, well, before everyone comes, we still have time. So so you're applying for jobs now, just to continue the.
Yeah. I mean, I'm applying a lot of positions, not only faculty, because I have like kind of the feeling that I would like to gain also a bit more experience on different topics. There's a lot of advertisements on now with massively multiplexed spectroscopic surveys like DAISY, Foremost, and of course maybe more close to you, WEAVE.
WEAVE, yes, exactly.
Yeah. But also like I got like now, well, this is not official, so but I'm shortlisted for interview with a faculty position.
Oh, good.
But that's in India, so.
At IUCA?
Yeah.
Okay, yeah, it's a beautiful place. It's a beautiful institute. Super.
Yeah.
Beautiful. I was there once. I visited for 2 weeks. We had a workshop there.
Yeah.
In fact, it was on MUSE while I was in Lyon. Yeah, it was. There's this Indo-French workshop series that every year it's either in France or India.
Yes, and, this is where the connection was established between the MUSE consortium, members of the MUSE consortium, and some researchers from IUCA.
Okay.
This is how I got also in touch with them, and then I immediately asked about possibility, and now they had some openings, and yeah. Well, it's not official yet. I just got like an unofficial word that there will be an official mail sent out, and if I would be available on the dates that they're scheduling for the interviews.
Okay. Yeah, and India is making some big investments in
exactly. With the UV satellite, this I think is very interesting. I don't know, you might have heard of the AstroSat mission that is running now.
Yes. In fact, one of their postdocs is coming to CEFCA in 1 month. She got accepted here for a postdoc. Yeah, she's coming. Yeah, with experience in AstroSat, she's coming here. That's
nice. Yeah, so this is of course what I'm really excited about. But then a bit more, and not in the distant future, there's the AstroSat 2 mission, which will have I mean, this was basically just the prototype, and it works already so well. So the next thing will be really a real telescope in space, not just a 30-centimeter aperture.
Exactly.
Yeah. And there will be, I cannot talk about this more, but there are some really interesting papers coming with AstroSat and MUSE. They're currently embargoed, so I cannot.
Okay, yeah, no problem. Yeah, I know. Kanak Saha was really
exactly
still the connection point, right?
Was my connection to because he worked with Anne also, Anne Verham.
Yes. Yeah, great. Yeah, and the institute is beautiful. It's just the architecture, the garden, the people. Yeah, it's really nice. Yeah.
So on my clock it says half. There's also, I see my student is online already. Anna is my master student.
Okay. So you mean that she needs approval? No, she can come, right?
Yeah, she's there. I see her already on the list of participants.
Yes, exactly.
It's basically the only participant I see right now.
Okay, yeah, online it's only you and me and Anna, but in the room so far, yeah, around 10-15 people have already.
Okay.
Have already come. I think we can start. Yeah, to be on time. Okay, so oh no, what happened? Okay, if I move the table, the connection to the projector gets weak. I should be careful. Okay. Okay, so thank you very much, everyone, for coming. It's my pleasure to introduce Christian Herenz. So he's Edmund Christian Herenz, the full name. So I met Christian first in 2016 when he was finishing his PhD, right? He just moved to Stockholm.
Yeah. Sounds about right. A bit before, I think.
Yeah, it was October 2016. It was the first MUSE collaboration, that meeting that I went, and Christian was there, and I really enjoyed it. I learned a lot from him, and he has a lot of experience with MUSE. So then, yeah, he got his PhD with Lutz Wysocki and Martin Roth from the IAP in Potsdam, and then he went to Stockholm. So and worked with Matthew Hayes, again focused on MUSE, right? And then after that, he went to ESO and he got an ESO fellowship at Santiago in Chile. Yeah, and now as part of the ending of the ESO postdoc, he's a researcher at Leiden University, and we look forward to good news about new positions soon.
Hopefully, yes.
Yes. Okay, so thank you very much. Today he'll be talking about this nice paper that came out like last month almost about a giant outflow from a tiny galaxy. So Christian, please go ahead.
Yeah, thanks, Mohammed. And I also have to say that I learned a lot from you during all the time, and also from your awesome GNU astronomy package. Not only the software is very useful for everyday data wrangling in astronomy, but also the effort you put into writing a documentation is really great. And thanks for inviting me to this talk. So I'm talking about the giant outflow from a tiny galaxy. And in the second part of the talk, I will present a new paper that I just put on the archive recently, is now in revision, about finding emission line galaxies in integral field spectroscopic data. Okay, so let's start with the first part of the talk, a 15 kiloparsec outflow cone piercing through the halo of the blue compact dwarf galaxy SBS 0335-052e. So this is a paper that is right now in press, and I just would like to highlight that the second to the fourth author were undergraduate students that were either funded by the NSF or by ESO to take part in this project, and it was really a joy also to work with the next generation of astronomers on this project. Some of them now are in PhD programs. So to motivate, to set the scene a bit, we have a big problem in cosmology and extragalactic physics, because most of the universe, we don't know actually what it is. We have the main constituents are so-called dark matter and dark energy, which make up most of the material in the universe, and the upcoming big, large spectroscopic surveys are going to address this problem by actually measuring the dark energy equation of state, or the equation of state, and then maybe we learn a bit more about this, but we will use galaxies as tracers, and in order to understand galaxies, we need to understand basically the baryonic physics, and here is basically where the stuff is happening that we are going to talk about in this seminar. This intergalactic plasma, the circumgalactic plasma, where a large fraction of the material in the universe is, and then stars and planets only make really a tiny fraction, but they're of course important for us. So the relevant baryonic constituents for this talk are the interstellar medium, which is characterized by densities between 1 and 100 per cubic centimeter, particles per cubic centimeter, and the typical temperature there is 10 to the 4 K. Outside the main stellar bodies of the galaxy, we find the circumgalactic medium, which is characterized by lower densities, lower than 1 per cubic centimeter, and here we also start to find higher temperatures up to the 1,000,000 Kelvin. And then if we go even further outside, we have the intergalactic medium outside of the visual radius, which is characterized by extremely low densities and high temperatures. So rather than characterizing the things by their position, it's a bit more physical, I think, to characterize them by their by the temperature and their densities. And so the first thing that we can observe here is the warm neutral medium, which is about 10 to the 4 K, but this is a neutral medium, so it's not ionized, and this is typically intermixed. The exact way this is intermixed with the warm ionized medium is not well known, but then we have in this phase basically the warm ionized medium, the diffuse ionized gas of similar densities. This has not to be confused with the similar temperature phase of the H2 regions, which have a much larger density. And lastly, also very important is the hot ionized medium, which is more than 1 million Kelvin and very low density and extremely hard to observe. But the warm neutral medium we can observe, for example, in 21 centimeter with radio telescopes, and the warm ionized medium, as we see in this talk, with MUSE. So we have the interactions between, so galaxies are not island universes. In order to understand basically the way galaxies evolve, we need to understand the interactions between the interstellar medium and the intergalactic medium. These are mediated through the circumgalactic medium, and they're basically 3 processes that we can make out that are important. There's the one that is observationally a big challenge, and I think so far we only have indirect evidence, and we know that it needs to work. These are inflows of fresh gas into galaxies. You could fill a whole lecture about this. Then what will be part of this talk are outflows and winds, feedback effects from the star formation, and lastly, encounters between galaxies, both interactions with their environment, so that mass transfer happens from one galaxy, or even mergers. So here we're going to talk about outflows. I could say this, that is a key processes for understanding galaxies to all the mechanisms that are shown, but just since we're now focusing on outflows, they will have impact on the star formation history, the size, the color, the metallicity, the dark matter density profiles even of dwarf galaxies, and you name it. There's a lot of things that basically the feedback from stars that is exerted on the interstellar medium has an effect on the evolution of a galaxy. And a key quantity that the theory and the modelers would like to know, and that they also tell us in order to quantify how outflows work, is the so-called mass loading factor, which is basically the amount of mass that is being loaded into the wind divided by the mass that is being converted into stars. So, and then the modelers basically tell us that if we go to lower masses, so this is a plot where we show here the mass loading rate versus the mass. And if we go to lower stellar masses, like here we at like 10 to the 7, 10 to the 6, these mass loading should work much more efficiently, and much more of the much more material will be expelled from the galaxy due to star formation. Now, if we look at the different phases that I just mentioned, then the cold phase is actually not participating a lot in this outflowing material. Mostly will be in this warm ionized phase, and also a significant fraction will be hot gas. So this is what the theory tells us. But of course, we are observers, or I'm an observer. How can we observe outflows? And there are basically 2 ways we can do this. We can look at absorption lines. There are several absorption lines in the ultraviolet spectral range that can be used that either trace neutral or ionized phases. And I show here just an example of a C2 line from a recent paper from Matthew Hayes, where he also determined the age of the stellar population on this galaxy, and he found that the absorption line strength and also the velocity offset shifts with the age of the stellar population. So the interpretation here is really that there's an accelerating wind that with age of the starburst, which kind of makes sense if you put more and more energy into the wind. The problem is, if you want to convert this into a mass loading rate, ultimately, you have to make assumptions about the outflow geometry. And this is, of course, difficult because we don't know it. So that's why we need also direct imaging, because it constrains, in principle, the geometry. Problem here, this is very hard to observe because it's very low surface brightness, diffuse low surface brightness emission. One thing that I also like about this area of astronomy, and I show here the poster child galaxy M82, the outflow in M82, observed here in H alpha. This is a false color image of H alpha. It just looks amazing, and this is really a topic that you can also communicate to the public. So M82 is a nearby galaxy, and the outflow has been basically characterized with almost every telescope that can observe this galaxy across all wavelength ranges. So what are the state-of-the-art observational constraints on the mass loading rate, and how do they compare to the theoretical predictions? Well, here is the black line that is shown in this plot is from this simulation that I showed earlier, a relation that was fitted there. And here the data points are observational constraints, both from direct imaging. The squares are from direct imaging. I will talk about this in a second. And other things are from absorption line spectroscopy, the circles. And well, it's hard to make up a trend actually in this figure. And then maybe even most of the points that they show here are below the theoretical predictions. So are the cosmological simulations overestimating actually the amount of mass that is being loaded into winds in low mass galaxies? Is this relation that they predict, is this actually real? Well, maybe, maybe not. We don't know. I think a big problem here is that because it's observationally so difficult, there is still things that we are not properly accounting for in the observations. And in the terms of imaging, most of the data points that you actually saw in this figure, they come from a very heroic effort with H-alpha narrowband imaging and VLA 21 centimeter observations of a sample of dwarf galaxies. They really pushed in the low mass regime, but this was done with the Kitt Peak Observatory. Lots of nights they spent to get these H-alpha images, and then they characterized the outflows basically by the amount of ionized gas that is seen in H-alpha that is outside of the lowest surface brightness contour that is seen in H1, sorry, here. For example, in this galaxy, so everything that would be outside here is the mass then contributes to the mass that is in the outflow. And the thing is, with the 4-meter telescope, you don't get very deep in, even with these long integration times that these people used, you only get to surface brightness limits of 4 times 10 to the minus 18. And this, there's probably a lot of mass I would say that these guys are missing. So the point I think here is that with MUSE and maybe also with the KCWI on KEC, we now have really ideal instruments to map outflows spatially around dwarf galaxies, because these instruments have such an unprecedented sensitivity for low surface brightness emission. And for me, looking at the literature now, it seems that every starbursting dwarf that has been observed with MUSE shows large extended H-alpha structures. I show here 3 examples of dwarf galaxies, low mass dwarf galaxies, but still higher mass than what we are going to talk about next. So, and the stellar body is shown here as contours in this figure, and this is ESO-338. It has this large and very extended H-alpha halo that shows a lot of substructure. Similar situation, very complex situation also in HARO 11. The main stellar body is just confined basically to the center here of this picture, and then you have the this extremely extended structure that goes several times the radius of the stellar body. But also HARO 14, which is a bit more nearby with MUSE in a relatively short integration, people saw this kind of fountains that come out of this galaxy. So what do we actually see when we map the diffuse gas, the diffuse ionized gas? Well, we see the H-alpha line from recombination mostly. And if we have a volume V, then basically we can calculate the luminosity for that volume with this simple formula here, where epsilon is the emissivity that follows from atomic physics. And for recombination lines in H-alpha, or for the hydrogen recombination lines, we have 2 scenarios, basically, case A and case B recombination. And the difference here is that for case B recombination, we assume that the optical depth in the Lyman series is very low. This is a typical assumption, or it's 0 actually. And this is a typical assumption that provides us often with realistic line ratios. Whereas case B is basically that provides us with typical line ratios, whereas case A is not giving us the right line ratios that we observe in H2 regions. And then when you convert the densities into optical depths, you see also that this assumption of setting the optical depth in the Lyman lines to infinity, which is case B. Sorry, I mixed those 2 up. But if you set the optical depth to infinity, then we get this realistic line ratios. And so we can also map the diffuse ionized gas in O3. This is done via collisional excitation. It's a forbidden transition, classically, a magnetic dipole transition. And here, this is mitigated by the collisional excitation factor, which also follows from atomic physics. Now we cannot just take the density squared. We have to take the density of the free electrons multiplied by the density of the O2 species, of the ionized, doubly ionized oxygen, times the volume. The numbers here of this curve, they are significantly higher. So this is 3 orders of magnitude higher, or 4 orders of magnitude higher than the recombination of H alpha of hydrogen. The point, though, is that there's of course significantly less oxygen. So and that's why if you calculate this through, the lines will have approximately equal strength. So these are the strongest lines in the spectrum to map this. And if we look at the warm neutral phase, then it's of course the spin flip of the electron in the ground state. 3/4 of the neutral atoms will be in a state where the electron is up. And yeah, so the lifetime of this transition is extremely long of spontaneous emission, but since there's so much gas there, we can detect it with large radio telescopes. And here in this talk and also in this paper, I compare it with the really state-of-the-art simulation of a single galaxy, where they implement feedback really that what in cosmological simulations would be called the subgrid regime. And they track every particle, and an interesting thing is that they can track every particle and also see where it's coming from. Everything that is yellow shown in this figure here is particles that have come from actually from this interstellar medium, whereas everything that is more magenta is gas that was already in the circumgalactic medium and now has been advected into the outflow. And here I would like to show a little video also of this simulation, because I think it's very instructive to see how this works on the timescales also. So the star formation proceeds. After 5 megayears or so, we have the first supernovas exploding, and then at some points the disk breaks up the gas, and then it can stream freely. This is basically density here in projection. And yeah, this is the first video, and then I also show you the temperature distribution. Again, after 5 years, nothing happens for the first 5 megayears because it takes some time for the supernovas to go boom. And then yeah, here we see now that the gas that is coming out first is like this yeah, hot gas, and then also cooler gas is being entrained in this outflow. So yeah, this is instructive, but this is of course a model. And is this real? So the galaxy SBS 0335 at a distance of 58 megaparsec has been long recognized as a reference laboratory for understanding galaxies at high redshift. And this is because first it has a absolute UV magnitude that is well below the M star at high redshift. So it's one of these typical galaxies that we would expect doing a lot of the work during the epoch of ionization. It is low mass, it has a low star formation rate, and I think the kicker here really is it has this extremely low metallicity, and is actually for a star-forming galaxy still in the top 5 of the extreme low metallicity galaxies. Here his colleague, the neighboring galaxy West that was discovered later, where unfortunately we don't have MUSE observations of that yet, has even a lower metallicity. So this is really an interesting system to study star formation and feedback in extremely low metallicity environments, as we believe they are occurring in the early universe. So of course, then it was one of the first targets that was even imaged with HST, extragalactic targets. In the continuum, we start seeing some star clusters here. And in H alpha, we start seeing yeah, some structures outside of the star clusters, like this shell here. And this already tells us that their feedback effects are going on. An interesting result from these early studies with HST was that there is an age gradient, in the sense that the oldest star clusters are in the north of this system, whereas the youngest star clusters are in the south. And we see also that the feedback effects seem to be most prominent towards the north. I'm sorry, I have to, when I point, it looks always a bit strange because I'm mirroring myself here on the screen. So these feedback effects are strongest in the north in HST, and then we have something, and people believe this is a propagating star formation, basically that the oldest stars triggered star formation episodes in other regions in this galaxy. So let's zoom out a bit, and we now use the Hubble data and now also the new MUSE data that we obtained for this galaxy. So first, within 500 parsec, we see these star clusters that I just mentioned. If we zoom out now a bit and look at the H-alpha image from MUSE, then we start seeing this feedback effects, these shells that also show some variations actually in surface brightness. So we can think of like broken, that they are already a bit broken and that they leave material through, but that is basically where the HST noise floor comes in. Now, this is 2 hours of MUSE. You don't see the noise floor yet because the scaling that I chose here, which is basically also, it's a cyclic color map. So the inner one is comparable to the color map shown here, whereas the outer one is now going to the lower surface brightness levels. We see that this structure actually starts, in H-alpha, there's more diffuse gas to be seen with interesting morphological features like these pointing fingers here and these spikes that are coming out. If we zoom out a bit more and adjust the color stretch, this gets gigantic. Yeah, we were just looking in this region here in the center. If we go out now, we see this large structure with the 2 very prominent filaments emanating to the northwest of this galaxy that then continue into a more frothy or lacy structure of really diffuse low surface brightness emission. There's also low surface brightness H-alpha everywhere, basically, around this galaxy. There may be 2 filaments pointing in this direction here. And the contours here is H1 observations, the warm neutral phase, that seems to be entrained actually in this structure that is going to this direction. So this is the neutral phase. And this is really spectacular and has not been seen in this galaxy. And I was thinking actually quite a long time, what is this actually? But now maybe the radio data, we can do a trick to get a bit better picture of the large scale H1 environment. This is called tapering, where in the UV plane during the observations, we downweigh the longer baselines. Of course, we decrease the sensitivity because we don't have the full set of antennas equally weighted anymore. But the increased beam size allows us then to also resolve structures at larger gas reservoirs around the galaxy at similar column densities. And we see really that this is a merging system of 2 galaxies that are close by each other. And then there is kind of a bridge between those 2, but the halo is elongated into this direction. So if we compare now the morphology of the H1 and the H2, we see that a lot of this ionized gas here is emanating outwards of this structure. This is maybe the first clue that we are dealing with an outflow. We also detect the structure in other emission lines in H-beta and in O3. And let me remind you, this is just 2 hours of MUSE integration that are being used. Well, it's 2 pointing, so it's 4-hour total observing time, but the depth in the outer parts is just 2 hours. And then we can basically have now 3 lines. Well, we can do some basic characterization of the physical properties and by analyzing the line ratios, which I did here in the eastern and the western filament. And that was the first thing where I thought something is really strange here. This is H-beta over H-alpha, so the inverse Balmer decrement. And the classical value that you would expect would be somewhere around here where I'm pointing. These lines are actually already case A. So even a lot of the data points don't even match up with case A recombination. We have a Balmer decrement that is much higher than what would be, much lower than what would be expected in the classical case B recombination scenario. If we look at O3 over H-alpha, this is hard to interpret, but the 2 filaments are characterized by different ratios. The eastern one has higher ratios, around 0.6, whereas the other one is around 0.3. It's hard to interpret because it depends on the one hand on the ionization parameter, how much ionizing photons do I have that can actually excite the oxygen, but it also depends on the amount of metallicity. And if we go back here, we see that this filament where the lower ratio is covered by more neutral hydrogen, well, which could do both actually. It could lower the metallicity in this region, but it also could lower the ionization parameter because I have just more material there to ionize with the same radiation. So anyway, this ratio, as I said, the H alpha over H beta or H beta over H alpha that I took here, because H beta has so low surface brightness, so I put H beta on top to not bias the measurement by the errors, is incompatible with the classical case A, where we have the optical depth in the Lyman alpha is 0, and the Lyman lines is 0, or case B where it is infinity. So I plot this here as a function of temperature, and we are actually somewhere in this regime here. So and I checked everything, data reduction, everything, extinction correction. So it's definitely not compatible with the case A or case B. But I think it's because we are in a region where we are not really at case A or case B, where we're at the we have to take into account the finite optical depths in the Lyman lines. And that actually alters the populations in the recombination cascade. And then you can reach ratios. And since we're in this diffuse ionized outer circumgalactic medium, this might be, these old theoretical calculations might actually be a clue to interpreting the ratios there. Of course, better photoionization modeling would be required to really prove this. So let's look at the kinematics from integral field spectroscopy. We have this nice kinematics. So there's clearly a gradient here from the southwest to the northeast. That was previously interpreted as a disk-like rotation in conjunction also with the H1 kinematics that we see in a second. There is a strong disturbance of the velocity field in the center that is likely due to feedback effects from the stars themselves. People were able to model this, and they say, okay, if we see a disk here, if we really want to see a disk, it goes into that direction, and that would mean that the minor axis to that disk goes into this direction. This is a dotted line shown here, and this I take from the literature, and I put it on just on the photometric center, and then I see that these filaments are bifurcating symmetrically with respect to the kinematical minor axis. And this is something that everybody who models or studies outflows tells you also, that these often go basically away from the disk of the galaxy. Of course, I mean, this is where the material will flow. This is where the force can act best to move the material out. So this is, I would say, a clue. What is weird then, though, is that the line width actually is really, really narrow. It's almost unresolved in MUSE. So really narrow lines. This is a bit weird, because if we expect that this material is flowing out, then we would expect it also to be turbulent, and this seems not to be the case here. So, well, let's roll with it for a second, and I think this is something we can discuss afterwards. So what I thought, maybe let's assume a structure that is kind of a cone inside a cone. So we have a cone that is filled with hot gas, which is surrounded by a wall in which the ionized gas, the warm ionized gas is. And then you will get something like a limb brightening effect under certain projections, where basically you have two things that are very bright that are filled with something that is of lower surface brightness. Well, for such a structure, just now to check if everything here makes sense, we can calculate the volume quite easily. We need to know the opening angle, but that are all things that we can get basically from the observations. I don't go into detail here. You can read this off the figure basically. And then we would get a mass, sorry, the pointer is a bit difficult here. We get a volume of 256 kiloparsec in the filled what is the empty volume or filled with the hot gas in this assumption, and the wall structure would be 142 kiloparsec cubic. And now let's put in some reasonable assumptions for the density. Well, I mean, we know that there are, or the simulations tell us there are variations, like gradients with the density to be expected and so on. And but okay, for the toy model, just assume now somewhere between in this range. Then we get a mass, which would be that in the hot volume, we would need to have a mass of like 10 to the 6, which would mean that we have a mass loading factor of in the hot phase for the star formation rate of 1 year of about a tenth. And then does it still make sense also? Can this structure be actually blown by the stellar population there? I think so. So we have 5 megayear delay. The stellar populations are roughly 15 megayears, the oldest ones there. So we get a velocity of around 1,600. Yeah, well, this actually is also compatible. Well, maybe a bit high, but compatible with the flow speed that is expected for this type of galaxy if it is powering an outflow. So this is very encouraging. Let's look at the observability of the structure. Now we need to make some assumptions about the density and the temperature actually, so that we can plug in this for the emissivity, and then we can simulate the structure, which I now aligned so that it matches a bit with what we see. And I think here you would agree with me that those panels here are close to maybe what we are seeing. So that would be like 10 to the 5, 5 times 10 to the minus 2, which would correspond to masses about 10 to the 8. And this would require mass loading rates for the ionized gas of greater than 10. In very good agreement, actually, encouraging agreement with what the modelers tell us what we have to expect for such a galaxy as a mass loading rate. And I think, and this is a bit cheating now. Now I plot the contours from the observations and over the model. And well, it reproduces somehow some of the basic morphological features. Of course, a lot of the finer structure here is not really reproduced. But since we already seen, and also the high resolution simulation, these structures are much more complicated and than such a simple structure. But I think it's very encouraging to see that this makes sense, which leads me to believe that we're actually observing here an outflowing structure. So the summary for this part of the talk would be that, yeah, this galaxy shows these very low surface brightness filaments that were previously undetected and could now be revealed via MUSE. The Balmer decrement is not compatible with what you would expect in typical ISM conditions. So it's indicative of a low optical depth in the Lyman series, but not 0. And the direction, and I think the symmetry also with respect to the kinematics of this galaxy can be interpreted as a clue for the outflow. The only thing that is strange is the narrow line width. And I think what is happening here is that we're seeing actually gas that is not being expelled directly from the galaxy, but this is gas that is in the halo of the galaxy and that is now being evected into the outflow. And this will have only a very short lifetime. So the kinematics that we see, or a short time where it will be observable in H alpha before it becomes hot. So we see basically the kinematic imprint of the neutral phase still. And if you compare that actually with the line width that we see in 21 centimeter, this you can look up also in the paper, then this makes sense. But I think we can discuss this a bit further. So now I would like to spend the remaining 15 or 10 minutes or so, I don't know, I think 15 minutes, to talk about something that is very dear to my heart, is finding such type of galaxies at the highest redshifts in deep integral field spectroscopic data. And this is a paper that I just put like on archive in December, and now there will be the revised version coming this week. So what is actually the problem when we need to find something? So it's a source detection problem, and just to formalize this a bit, let's look at the 1D case, where we have, we are looking for some line profile that can be described by this vector S. And this is somewhere embedded in a noisy data vector. And the noise is given by a Gaussian noise vector with 0 mean. It can have covariances for now, and then one can basically create the vector like this if it needs to be created in a simulation. And source detection is then basically a hypothesis test where we have like our null hypothesis is there is no source. That means that F is basically equal to the noise vector N. Or we decide then with some reasonable criterion for the alternative hypothesis that actually a source is in there superimposed with some amplitude A. And what is the best criterion to do that? That's known as the matched filter and is basically a scalar product between a vector called T and our vector F. And T is called the matched filter if it is basically the shape of the profile filter, but weighted with the inverse of the covariance matrix. And then we can choose a convenient normalization for that, which is given by this expression here, which basically gives us a decision criterion that is very reminiscent of what we like to call a gamma or kappa times sigma detection. So 5 sigma or something we can believe, and 2 sigma is a Nature paper. But this is only relevant basically if, or only formally correct if the position is known a priori, which is often not the case when we are looking for blindly for a line. But then we can calculate a vector with these test statistics. I don't go here in the details. This is basically given as a scalar product. And the point is, especially if the noise is uncorrelated, then the matched filter has a very simple expression here. It's basically the profile weighted accordingly by the variance spectrum. This can be generalized to 3D very easily, but computationally this is hard because this would now have to be calculated for every voxel in the data cubes. We can make a trick by separating the profile. Now the problem was, because it was so hard in the original software that I wrote for source detection, LSD-Cut 1, I did like a simplification of this formula. The problem is that this approximation does not work well if there's a spectrally rapidly varying variances, which we will see in the red part of the spectral range. So in this plot here, I show the ground truth of like an idealized test setup. We have an emission line. And then there's almost constant noise just in the wings of this line. The noise is increased. This is one particular realization of this setup. You clearly see that the line is buried in the noise. Well, if we use this approximation that I used in my original implementation of the source detection algorithm, we never get above basically a threshold of 4 in the final signal to noise. Whereas if we now do the weighting correctly for the rapidly varying variances, this line would be significantly more detectable. So of course, okay, I won't go really now in the details here, but this can be, the only thing that we need to assume now basically is that the noise is not depending on position, or that it can be rescaled as a position of, as a function of position. And now I tested this on the MUSE-wide data release. That was the original data release was done with the LSD-Cut 1.0. That was a software that I developed during my PhD. And now with 2.0, we see that a lot of the lines, especially in the vicinity of the skylines, increase their detection significances significantly. And also here, if I plot this as a histogram, especially in the red part, a large fraction of objects gets an improved signal-to-noise ratio. One cool thing now about this new LSD-Cut 2.2 algorithm for detecting faint emission lines in integral field spectroscopic data is that the selection function becomes deterministic. That means we don't need to rely on source insertion and recovery experiments to know the exact depth of our data in this search, but we can calculate it from the variances of the data and the property that we put into the filter. Yeah, I mean, the talk has been going on for some time, so I go just show here this formula basically. That is then the expression that we can use, and it boils down to the determination of a proportionality factor to the flux that this function is fully determined. And the idealized case is you just plug into the matched filter a source that is matching exactly the matched filter at known flux, and then you basically get an expression for this, which you can plug in. Yeah, so we have our selection function here, the analytic expression with this value for C, and this is the calculation. In the left panel is shown the calculation with this formula, and the C is shown here for a search of Lyman alpha emitting galaxies in the red part of the MUSE extremely deep field, here shown as a function of wavelength and limiting flux. 0 is we don't detect anything. Everything that is white we detect, and then we have this intermediate regime where it becomes a stochastic question. Of course, this looks nice, and then we compare it here to the experiment where I really went now and put in sources in every layer and recovered them later with LSD cut, and then this looks already very encouraging. I mean, it's I don't see any difference. Of course, we can plot the difference. There is a little bit of difference between the analytical curves, which I also show here for several spectral layers. The analytical curves are shown as dashed lines, whereas the insertion and recovery experiment at 4 different wavelength layers is shown as a red line. And I did not pick here the best ones. Actually, I put ones that show up really red here. But still, for practical purposes, this can be neglected. The upper plot also shows the difference in the 50% completeness limit from the analytical prediction and the experiment. And again, the differences here are like really on the sub% level, and they are random. They're not correlated with features in the skylines or something. So this is nice. Of course, this is now the idealized case. We know that when we recover sources in the or that real sources will never be of the same three-dimensional appearance in the data cube than the source that it was assumed for the matched filter. But this can also be accounted for by some rescaling of this C of lambda factor with a factor that I call psi in the paper. And I show this here for different types of Lyman alpha halo profiles at high redshift. We know that the halo fraction, which is shown here, a halo fraction, and then the factor psi. And we know that there's like around 60 to 80% halo fractions in these high redshift galaxies. And then we lose a bit of flux for these type of sources. We need to basically rescale the selection function by 1 over psi. But the interesting thing, which I show you in the second panel, is the loss in signal to noise with respect to the signal to noise that we would have gotten if we would have filtered it with the perfectly matching source, also this halo type of profile here. And we don't lose that much signal to noise. So this Gaussian filter is a good all-round filter for also to detect these halo lines. The Gaussian filter that was used here for this particular search, I have to say. Yeah, and that's basically finishing the second part of my talk. I think I'm a bit early on time, actually. But just let me read the slide for you. This LSD cut 2.0, watch out the paper. This week, I think I will, or next week, the revised version. The referee was quite good on that, I have to say. Even if it's like a small journal, he really took time reading this and improving the paper a lot. So don't read the version that is on right now. So yeah, we have now an improved algorithm that can uncover lines also better in the red part of the spectral range. And the good thing about this algorithm, and why I like this for population studies now, like luminosity functions or clustering functions of Lyman alpha emitting galaxies, is that it's deterministic. So if the data behaves well, we have the selection function. Of course, we always need to check if it behaves well, but for the deep MUSE data and also the shallower data sets, like the MUSE wide survey, it works really good. Yeah, that's basically it. I would like to stop here now.
Thank you very much. Thank you. So is there any questions here? in the room? So I can start with one and then hopefully get more discussions going. So this galaxy, this low mass star forming galaxy that you said was studied early on with Hubble, right?
Yes.
So what was the selection criteria that it was one of the earliest, well, studied from the late 90s, right? If I'm not
Yeah, also, well,
so how did they select this object? So what was the...
So, okay, so originally this object was found, that's why the name also comes from, in the SBS survey, that was the second Buiran observatory survey, which was an objective prism survey, like a low resolution, GRISM, you would say nowadays, what they do as GRISM surveys with HST, and it showed up as a blue object, and it didn't have any AGN features. And that's why then in the 90s people took like a deep spectrum. I think so. It was before it was observed with HST. People took a deep spectrum with I don't know now. It could be even the Russian telescope. I think it was the SAO telescope. Yeah, the 6-meter telescope. They took a spectrum and then they deep spectrum and they analyzed all these emission line ratios and. This is this group around Yuri Isotov that is also now very famous with the research on the green P galaxies and the Liban continuum leaking galaxies in the local universe. So they have a very good way of determining the metallicities. And after they found that it has extremely or signs of a low metallicity, it became like one of the first galaxies then as soon as Hubble launched. So it was 1990 was the publication of the metallicity, and then I mean there was no Hubble there yet, so it took some time. But it was naturally one of the first targets where, that was in the first GO call for imaging to study the stellar populations, resolved stellar population study. But that then revealed. I mean, in the beginning they were not doing really population studies; they were just looking at the color gradient. Nowadays, with the stellar population models, we can do it a bit. Well, we still look at the colors, but we compare them to a bit more sophisticated models that give us ages.
Exactly. Yeah, the reason I ask is, with the survey we're doing here with JPass, we're observing thousands of degrees with narrow bands.
Yes.
And we've already found a very large number of green peas, for example. Unfortunately, Alessandro's not here today. I'm sure he would have had some interesting discussion points on this. And cases like this can be found. Hopefully, we can find many such cases once JPass.
Yes. So I mean, we know a lot of blue compact dwarf galaxies that are suitable for this type of studies already. But especially, I think one criterion that we need to look into is the metallicity. So because I think one of the reasons that this galaxy shows such a spectacular outflow is that it has such a large neutral gas reservoir that has not been used and that can be evected into the outflow and then shine relatively brightly because the density is just there. So I think metallicity, looking for compact star-forming galaxies at low metallicity is what we would like to have a sample of. And actually, we did this with the Subaru strategic the survey that they are running also on Subaru, and there the good thing is these targets are in the south, right? So and we can follow them up with MUSE. So we're right now assembling 24 galaxies that have been selected. I mean, there's some famous ones that were known already before, but also some new ones that have similar properties and are some are a bit more distant, some are a bit more closer, and we're using some bad weather time on with MUSE to get like a larger sample and see if this, because this is just one object. But as I said, like the other ones that were also targeted, not even for this purpose, and then also the authors often don't even comment on these, like well, they comment on these structures, but they don't interpret them in the sense of something like an outflow.
Yeah.
Yeah, we're trying to do this a bit more systematically now.
In
Yeah.
those cases that you've studied the similar galaxies, what fraction of them had such well, maybe not as extensive as this one, but just approximately?
I don't know yet. I mean, the statistical question I cannot answer right now. This is why this was the main motivation why we said we're selecting a low metallicity sample with a well-defined criterion, compactness and a specific star formation rate and blue colors. Which would be, I mean, in the classical sense, blue compact dwarf galaxies, but now these are like found with the 8-meter telescope and a narrowband types of survey. So yeah, so I think not there yet. I hope when we speak in 2 years or 1 year, you ask me this question again, and I can give you a number that then of course depends on the bias with how we selected the galaxies. So I really encourage also other people to construct samples maybe and to look for this, because I mean the other way, and I think at high redshift we're really limited to the absorption line technique, but then we need to somehow convert this into geometries. And I don't think actually this example that I showed from Hayes, this letter that he recently had, he just assumes a spherical geometry, for example, and it is very hard to conceive outflows on that scales being spherical, because the mass distribution of the regions where the stars are forming will be elliptical, triaxial, you name it, and that will naturally create some beaming effect in the end that the outflow will go into like a more confined region of space.
Yes, thank you. So Helena had a question. Helena Dominguez Sanchez is staff here.
Thanks a lot for the talk. It was very interesting.
I hear you very not very good. If you maybe can go closer to the microphone.
Hello. So,
yes.
Can you hear me now better?
Now, wonderful. Yes.
Okay. So I said, first of all, thanks for the talk. It was very interesting. And secondly, apologies if you already answered that question, but I had to leave for a quick call. Do you know, or do you have an idea of the origin of the outflow?
The origin of the outflow. It's, I mean, you mean if there's something else than the stars?
Yeah, exactly. Is it supernova? Is it?
Yeah. So I mean, as I showed in my, I showed like this model calculation is consistent if this little toy model that I built up, right? In order to get some realistic, it's still a bit too high. But in order to get a realistic wind speed, I basically take the age of the stellar population. I mean, just from this study, I take the oldest, which are like 15 mega years, and then I assume, in order to make it match, I assume the delay for the onset of the supernova explosions, which is commonly assumed to be 5 mega years. I mean, I don't know if this is true at low metallicity, but at least Starburst 99, if you look at the models in Starburst 99, they agree with this 5 mega year, and then that makes sense that this is being completely driven by supernova explosions. Yes.
Okay, thank you. I think I missed this slide. I'm sorry about that.
Okay. Yes. Thank you. Thank you.
Yeah.
So, if there's no other questions, maybe I have one more about O2. How about O2? Is this because you talked about O3 but not O2? We would expect.
Yeah, why did I talk not about O2? I mean, it's not in the MUSE spectral range. I mean, I would love to see.
Okay, so yeah,
that's why we need to build Blue MUSE.
Yes.
Or
yeah. How at what was the distance? I forgot the distance. Okay.
It's nearby. The redshift is not important. O2 is just I mean the redshift is it is cosmological.
It does come in at pretty low redshifts with MUSE, but yeah, not
there yet. No. This is basically, I mean, it's not the redshift 0 universe. We're already in the Hubble flow, but So the distance that I quote, the 58 megaparsec, is also just the cosmological distance.
Okay, 58 megaparsecs.
Yeah.
Okay,
So it's quite far
I missed the
away.
distance.
Yeah. But so in the sample that we've
Okay.
constructed, we go up to 100 megaparsec and down to like 20 megaparsecs. So this is, I mean, this is a problem with MUSE, yeah. And
Yes.
I don't know if it would be valuable to take like long slit spectroscopy. I mean, it would be the next strongest line, so to say, right? That we expect. Yeah. kpc-scale. I need to convince maybe people. I saw some people, they are starting to look also now at H alpha halos. As there was
I saw a few papers on H
yeah. So I think this is being recognized as interesting. Yeah.
Exactly. Yes. Okay. So if there's no more questions, we can stop the meeting. No more questions.
Thank you so much.
Thank you. Thank you for the really nice talk. And so I'll be in touch about some further discussion points.
Yeah. And I mean, if you have any questions, you know, about the paper or anything, just write an email. I'm happy to discuss this further. And
Exactly. Yeah, because we already have a sample of around. I think a recent paper came out with J+, our smaller survey while J+ is coming, and it had 400 green peas. And some parts of J+ actually are visible, so they're at a declination of less than 10 or something.
That is visible, yeah. It's not perfect, but I mean, not everything is served on a gold plate.
Exactly. So we should talk with Alejandro I should get you in touch with Alejandro, because unfortunately neither Alejandro or Juan, which are working exactly on this, are here today.
But we can make a test because they promised to watch the videos. So if you watch the video,
exactly.
Write me an email, please, and then we can think about it.
So that sample, hopefully there should be some cases that are new, because and then we can see if we can watch them with MUSE.
Yeah.
Okay,
so I mean,
so much,
Okay, thanks. I mean, we could talk hours about this. I'm concentrating on my sample now, and then we see. We will see, and I think in a year or two we can answer the question that you raised as the first question.
Yes, thank you so much, and good luck with the rest of your stay in Leiden.
Thanks.
Thank you. Have a good day.
Thank you so much, Mohammed.
Bye.
Thank you. Bye.